2 of Stokes' theorem. It's still Stokes' theorem. I did rearrange the numbers, so they're now called 1, 2, 3, 4. That doesn't affect anything. If you've done a question, it's still there. It just might be called 7 now, not 2, whatever it was called previously. What we're being asked to do here is to find this surface integral, the curl, that guy there. And Stokes' theorem says that you can take a double integral surface integral and convert it into a single closed loop, single integral. Right, the little circle closed loop, so it starts and finishes at the same point, and FDR. So F is going to be the vector field, which will be told in the question, and dr is essentially the parametric curve R of t. So if you imagine this green thing being the surface, if you imagine this green thing here being the surface, then this red squiggly line is the boundary curve, and that boundary curve is what R of t is. So what we're going to have to do here is find essentially just one thing, which makes life a little bit easier. We need to find out what the parametric equation is of the boundary curve for each question, because once we know that, we'll be able to calculate this, because this guy gets turned into that. It's the vector field where all the x, y, and z's, all these guys here, are turned into t's, times the derivative of this fella, dt. So it ends up being essentially a single derivative. And this will be almost, I think everyone or almost every question ends up being a circle. So it's going to be from 0 to 2 pi. And R of t then is the boundary curve of the surface. So we are going to create a 3-dimensional R of t. It's not as hard as it seems to generate this thing. It's going to be 3 guys. And the reason why it's not going to be too bad is that one of these 3 guys is either 0 or a number, and the other 2 are a circle. And if you want to generate a circle, we can just do the cosine t, sine t situation. So let's start with, let's start with this one, question 1. Matthew, you said it's the new question 3. Would that be a good one for me to do next then?
Yeah.
Okay.
I think I just forgot how to do line integrals.
I'm going to have to go in here and change some things, and I'm talking loud so we don't hear whatever that person is talking about, because it's not our business. There we go. Whew. Right, that's back to our thing. Right, in question 1, as in all 4 questions, you're being asked to find this surface integral. They have told you who f is, which is fine because they have to. And they're telling you the surface S is this guy, and they're telling you it's above the XY plane. So what they're really telling you there is that Z equals 0. Now, step 1. Is find the boundary curve C. Well, if you take the surface, in this case, this guy here, and you make it on the XY plane, you're making X equals 0, sorry, Z equals 0, and you are getting that guy. So I know what this curve looks like. It's basically a circle of radius 3. And so I'm going to make X 3 cosine t's, and I'm going to make Y 3 sine t's, and I'm going to make Z 0. And that is my space curve. 3 cosine t, 3 sine t, 0. I could have switched places with these two, And if I did switch places with these two, I would change the orientation. But I've given up trying to do orientation because it seems to be not 9 times out of 10, it doesn't seem to matter because the answer is positive. So if I end up with a negative answer, I'll just make it positive and that'll cure it. That's a kind of cop out, but that'll work. So just pick cosine and sine every time and go with the flow, right? Well, I need this guy, which is great, but I need him because he's going to be here and he's going to replace these three guys, right? Which in our case is going to be this expression using x, using y, and using z. So let's get the derivative. And the derivative, if you differentiate 3 cosines, is -3 sines. And if you differentiate 3 sines, you get 3 cosines, and 0 gets you 0. So that's good. And I should have put in here the start and finish. That's essentially the A and B. Okay, I think we've got all the pieces. We should be able to get it then. So this surface integral for the curl of f ds is going to be in the integral from t equals 0 to t equals 2 pi. This function, which I'm actually going to write down in terms of x, y, and z, probably don't need it, but it is for notes, which is that guy. Dot product with the derivative, which is -3 sine t, 3 cosine t, and a 0 dt. So it's going to be the integral from 0 to 2 pi. X is that guy, but sine of 0 is 0, so I don't care about that, that's 0. Y squared is this guy, and xy is this times this. Dot product with that guy, and 0 dt. 0 times that gets you 0, so it doesn't matter. 9 times that guy gets you 27 sine squared t, cosine t, then bump. And at that point, we'll do a dot, dot, dot in it, right? You agree it's a U sub and you do what you need to do. Are we good with number 1? Let's jump to number 3. What's going on in 3? Okay. In question.
I just want to say I was only having a time with it because I did forget how to do line integrals for a second. So.
Okay, it doesn't matter. It's a good question. I have no problems doing it. It doesn't matter. Hopefully, it'll come back to us. So in this case, it's an inverse tan of x squared y z squared. Ugh. I don't like this one. I've only written down the first piece of it. Then you got this guy. And then you've got this guy. And there we go. Now the surface is described in this format. And it's using x's between these two guys. So we need to figure out what does that boundary curve look like. Well, if you put x equals 0 in here, I get that guy, which really doesn't tell me anything because it just means everybody is 0. And if I put in 4 here, I get that guy, which gives me y squared plus z squared. Interesting. So that is a circle on the YZ plane instead of the XY plane or any other plane. And that's not going to put me off too much. I'm just going to do 4 cosine t. I'm going to do z is 4 sine t. That'll make the circle arm. And then I just need to figure out who I'm going to put in for x. So where was what's x going to be? X is going to be 4. No point using that because everything disappears there, but that gives me 4. I use that side. And I'm going to do t goes from 0 to 2 pi. So my space curve is going to be x is 4, y is 4 cosine t, and z is 4 sine t. Are we comfortable with that? Okay. Now, while I'm at it, I might as well do its derivative because I know I'm going to use it. So it's going to be 0, negative 4 sine t, 4 cosine t. Bubble around it. Help me do it. So let's do some of these things outside the integration. Let's do this guy. He's going to be the inverse tan of x squared. Ooh. 16y. Oh, I'll have to do it again, sorry. Inverse, I think I better just do them in 3 rows. There's no way I'm going to squeeze all that into one row. So x squared is 4 squared, so that's 16. Y is going to be 4 cosine t's, and z is going to be that guy squared, so that's going to be 16 sine t, right? Sine squared t. Okay, that's just the first one. The second one is x squared y, so that's going to be 16 times that guy. And the third one was x squared z squared, so x squared is 16 and z is this guy squared, so that's 16 sine squared t. I'll try and see if I can get that into one line. 16 times 4 times 16 is just some ridiculous number. 16 times 4 times 16 is 1024. Oh, and that is good because I can see 1024. Inverse tan of 1024. That guy and that guy. So it's going to be a sine squared t, a cosine t, comma. This fella here is 64 cosine t's, and this guy is 256 sine squared t. Let's check that out. Yeah, and yeah, okay, we're good so far. Now, we're going to do an integral from 0 to 2 pi. We're going to do this guy dot product, and I'm not going to write that down again, with this guy. Do you see this horrible inverse tan of a mess? It's just going to get multiplied by 0. So after all that work, it was 0. Do you know if I'd saw that before I'd looked, I wouldn't even have bothered writing that down. I would have just said dot, dot, dot or something and just said, look, I'm going to multiply you by 0. I don't really care what you are because you're going to disappear anyway. Now, if you take the middle term, which is this guy, and you multiply it by that, you get negative, check it out, 64 times 4. So you get negative 256. Okay, that guy times that guy. So you're going to get a sine t, cosine t. And then this guy times this guy is going to get you 1,000, is it? Yeah, 1,024. And that guy times that guy is a cosine t, a sine squared t dt. So it's 0 to 2 pi, negative 256 sine t cosine t plus 1,024 cosine t sine squared t. And at this point, I'm ready to dot it. To do this integral, you're going to do a u sub, either u is sine t or u is cosine t, or you can convert it into a version of sine 2t if you prefer, and integrate that. In this one, you're going to do a u sub where sine t is your u sub, and you're going to get the answer. And now I've gone, I should look at the answers before I do things. Do you know the answer ends up being 0? Go figure. All that blinking work just to find out that the line integral is 0. I bet you that's a conservative field. But they didn't ask me to find out if it was a conservative field, so I have to assume the worst and just not do it. Okay. Does that look about right, Matthew? I don't know if you finished 3, but did you get 0 as well?
Yes, I did.
Did you notice it was a conservative field and saved yourself half an hour of work?
No.
No, neither did I. I guess it would have been unfair if they told us, to be honest, so that's fine. The next one I'm going to show you because it's a picture. So this is going to be question 4. There's only 4 of these guys, so if nothing else, I'll at least have done half the work for you, because yeah, it's a lot of work. Oh no, it isn't. Oh, this is not good. Should never put the answers on me. I don't like it because they help me a lot, and then they go and do what they've just done here, which I don't like. Okay, here is the question that we're interested in. Move that window out the way. Solving. It's the surface is S, and it has this equation here. And it meets up on this plane here, which is what, the XZ plane, right? And so just using that picture, although I'm going to have that picture in front of you, I'm going to be writing down what's going on here. In this picture here, if you wanted to give me the boundary curve, which is that edge here, what is the Y value? Every point on this white curve at the edge, what is its Y coordinate?
Is it 0?
It's 0. I think the problem, and it's my problem as well, aren't we more used to everything being on the XY plane, and so we're used to X and Y being the guys and Z being 0, but you can orientate these shapes any way you like. Now that we've got that out the way, if you look at it side on, can you see a circle? Right, now if you look at this equation and what, go away, right, and okay, I can't cover that up, but if you covered up that Y square, wouldn't you be left with 9x squared plus 9z squared equals 9? And if you reduce that, won't you have the equation x squared plus z squared equals 1? Are you comfortable with Y being 0 and that circle having the equation x squared plus z squared equals 1? We good with that? Right, now let me return to here. The parametric of that circle, you know, it looked like this, that one, is Y is always 0, and this is true. So I'm going to go and call this guy 1 times cosine t, and I'm going to call this guy 1 times sine t, and I'm going to do t goes from 0 to 2 pi. Are we comfortable with that? Now you put that together, then your space curve is going to have an x component of cosine t, a y component of 0, and a z component of sine t. Are we comfortable with that? And so the derivative of this guy, which is the guy we really want to use, at least in the integration piece, is negative sine t, 0, cosine t. And now I'm going to put down the vector field. And this guy is e to the 4xy. And this guy is e to the xz. And this guy is x squared z. And I've just thought of a little thing to help me out. It's going to be the integral over c. It's going to be f dot product r dashed t dt. And I'm going to leave these guys as x, y, z's for a little while. So 0 to 2 pi. E to that guy. E to that guy. That guy. Dot product with negative sine t, 0 cosine t dt. And that guy times this guy gets you negative sine t e to the 4xy plus 0 plus x squared z cosine t dt. And I just did that so I didn't have to turn all these guys into t's just to end up with a 0. I'm not sure now that I've seen it if it was worth doing, but I did it. So we have negative sine t e to the 4xy. Well, that's x, that's y. Try that again. That's x. Let's try it a third time. I should put bubbles around things. My scan is ridiculous. That's the x, y, z. It's the space curve that you use for x, y, and z. So 4 times cosine t times 0. So what does that get me? It gets me e to the 0, and e to the 0 is just 1, so that guy gets me negative sine t. The middle guy's nothing. Let's just write him down. And this guy is x squared, which is this guy squared, plus z, which is that guy, times cosine t. So I now get sine t cosine cube t. Probably made a bit more of a meal than this needs to be. It's going to be negative sine t plus sine t cosine cube t dt. And once we get to kind of that stage, I feel happy. I'll put on the answer now. Although I do know this, I do know the answer, but I don't know the solution. So let's just check that I got that bit right. Oh, well, that didn't help because it missed out too much lines of working, but I'm pretty sure it is right. And what do I dislike about it? It was 0 again. That's what I disliked about it. There's something sometimes unsatisfying about getting a lot of work done and then finding out the answer was 0 at the end. It just seems to me like, that was annoying. But it is what it is. It worked. So I think there's only one guy left. Perfect. Okay, let's wind back and do the last one then. So version of question 2. Let's focus on getting the space curve It's an x squared. I think, have I done this one? It's deja vu. Did I do the x squared plus y squared plus z squared 25, y is 0 one? Is that just me thinking I've done it, or have I done it? Nobody remembers. Let's assume then that I just think I've done it. Okay. If you take a sphere and you cut it at y equals 0, which is basically what's happening here, what you're going to get is x squared plus z squared equals 25, and we'll choose the y equals 0 as the boundary. And so I now have x is 5 cosine t. I have y equals 5. No, I don't. I have y equals 0. And I have z equals 5 sine t. So we got our space curve. X, y, z. And its derivative will be negative 5 cosine 0. Nobody knows that. Negative 5 sine. Let me check something. Oh, good. The answer isn't 0. Right, so we got our space curve, we got its derivative, that's cool. What's the vector function look like? It's z e to the y, x cosine y, and xz sine of y. Okay. Is it worth turning that into? There's my x, there's my y, there's my z. Okay, let's turn them into t's. It's going to be 5 sine t times e to the 0. It's going to be 5 cosine t's times cosine of 0 plus x times z times the sine of 0, which is just 0. And that makes f 5 sine t times 1. That makes this guy 5 cosine t times 1, 0. So we're going to be doing an integral from t equals 0 to 2 pi because it's a whole circle. We're going to be doing f, which is this guy. Dot product with the derivative of the space curve. Dt. That guy times that guy gets you negative 25 sine squared t. That guy times that guy gets you nothing. That guy times that guy gets you nothing. So actually, that's all you have. Let's check that. Okay, and they have an orientation issue. So I'll stick a minus in front of it to keep it happy. How do I know it's an orientation? That is one I've done. That's the one that said it was positive and it's not negative. Okay, well, I don't think I took it to the end, so let's do that. Tell you what, let's just keep that and see where it goes. I can always change it later. If you want to integrate a sine squared, the easiest way to do that is to reckon, well, let's pull out the negative 25, is to recognize that sine squared can be written as half of 1 minus the cosine of 2t. So it's going to be 1/2, take away 1/2 the cosine of 2t. integrate a half, you get that. If you integrate the cosine of 2t, you get the sine of 2t, positive that is, times a half, which gives you a quarter, and because it's positive, that sign remains as it was. So you're going to get 1/2 times 2 pi, take away essentially nothing, minus a whole load of nothings. So you get negative 25, no, they cancel. So you get negative 25 pi. The correct answer was 25 pi. It was positive orientation then that got me. So it's okay. I guess it's okay. It's 25. There's no indication in the question that the orientation was pointing in a weird direction. All it says here is the orientation in the direction of the positive y-axis. But evidently that's a negative orientation for some reason. I'm uncomfortable about not knowing for sure whether something's plus or minus. And there's no obvious way of doing it. So I think we just have to cross your fingers. If I gave you a question in the final like that, I would do either answer. I don't think it would be fair for me to say it has to be positive because it could be negative. I think it was you, Matthew. Did you say it depends on which side of the surface is positive?
Yeah, and in this question, I think you might have got it negative because you might have swapped around the sine and the cosine for x and y, so it might have been going clockwise instead of counterclockwise.
Okay. So when I did this guy here?
Yeah, because, or maybe.
Well, it's on a plane. It's going either this way or it's going that way. I guess I could have plotted it and found out.
Hold on. I did this question. Wait, I don't remember.
Okay, it's fine.
Yeah, but it might have been something along those lines. I don't know.
So I guess the bottom line is don't stress about not knowing if it's plus or minus. You're in good company. It seems to be a very nuancy thing. So let's spend what time we've got left telling you how good you lot are at getting through the course, because we are now on our last section. I'll probably be spending just a couple of days on that. That means that next week, apart from maybe Monday, Tuesday, is going to be all about revising for your final. So it's nice that we have this time. I hope that doesn't mean that I've maybe went through things faster than you would prefer. That can happen sometimes as well. Now, I don't want to do that yet. It's too early. Let's see if I can find something first. I'm actually going to show you what I'm typing. Divergence theorem in science. Put it in here then. And go for it. That doesn't. Maybe this. Let's see. I want to see if I can find why you would want to do it. In vector calculus, then, the divergence theorem, also known as Gauss's theorem, or I'm not even going to pronounce that guy, but he's probably a Russian. is a theorem which relates the flux of a vector field through a closed surface to the divergence of a field in the volume it's enclosed by. More precisely, the divergence theorem states that the surface integral of a vector field over a closed surface, which we call flux, through that surface is equal to the volume of an integral. What that essentially is telling us is that we can calculate flux by rewriting it in terms of a triple integral, i.e. a volume. So we've just been doing flux and turning it into a line integral, right? That's the last 4 questions, right? Now we're going to take that thing and turn it into a triple integral. Okay, why you want to do it now? The divergence theorem is an important result for mathematics of physics and engineering, in particular electrostatics and fluid dynamics. In these fields, it's usually applied in 3 dimensions, but it can be generalized to any number of dimensions that you want. And then it goes on to stuff I'm really not interested in. Have I convinced you that somebody wants to use this thing? And if you're going to be in fluid dynamics or electrostatics or some parts of engineering and physics, you may well come across situations where this theorem is going to get you out of trouble, or at least get you the answer to something. Right? Are we good? I think there's a video on the divergence theorem, but I can't find it right now. If I do, I will probably put it online and let you look at it. So, where am I? Oh, back here. So let's remind you the divergence part of the divergence theorem. If I asked you to find the divergence of a vector field F, and I tell you that F was P, Q, and R, can anybody remember how you get the divergence? What's the formula?
Derivative with respect to x of p, then the derivative plus the derivative with respect to y of q, and then like with respect to z of r.
And if you use the grad operator, isn't that essentially the delta, the dot product of those two? Right. So let's do that as a starting point. So suppose I have a function whose vector field, and I'm just copying one right out of the quiz here. It's a comma. That's a comma. If you want to find the divergence of this particular one, you would go differential, put labels on things. That's P, that guy's Q, that guy's R. You differentiate this guy with respect to X, you get that guy. You differentiate this guy with respect to Y, and you get that guy. And you differentiate this guy with respect to Z, and you get that guy. Are we comfortable with that? What happens if the divergence is 0?
Is it a conservative vector field?
Yeah. And what do you think is going to be the answer to the flux, which is this guy? It's going to be 0, So if you ever get lucky and the divergence is 0, will you just go straight to the answer, and the answer to the flux, which is this guy, is 0? Right. Well, yeah, I got time for one. Suppose I have a vector field, and I'm picking a nice easy one because we don't have a lot of time. Is that guy? And suppose that the region that we're talking about is x goes from 0 to 1, y goes from 0 to 2, and z goes from 0 to 3. So in other words, a little cube in 3D space. So in that cube in 3D space, there's a vector field inside it, right? There's a vector field, if you like, passing through it. And we want to know what the double integral of S of f ds, that guy called the flux. Well, he is a triple integral. And he's a triple integral of the divergence of f dv. And in this particular thing, this, what letter of the alphabet they're going to use, who cares? R. R for three-dimensional, right, region. In our case, it's going to be x equals 0 to x equals 1, y equals 0 to y equals 2, z equals 0 to z equals 3. I'll put the divergence in here, and then it's going to be a dz, dy, dx guy. Now, divergence, differentiate that with x, differentiate that with y, differentiate that with z. Are we comfortable about the divergence? Because I made a nice easy one. Essentially, you do that guy first, then you do that guy second, then you do that guy third. So let's see what we can get. If you add 1 to the power, you get z cubed. You add 1 here, you get 2yz. You add 1 here, you get z. So that's the integral from z equals 2 to z equals 3. And then after I get the answer to that, I'll do the integral from y equals 0 to 2. And then once we get the answer to that, we'll then do the integral from x equals 0 to 1. Righty time. As long as you know the limits or the bounds of integration, isn't this going to be a lot less work than anything else we've done? So in a funny sort of a way, we're finishing with a relatively easy process. Triple integral. Tell me the x, y's, and z's, right? Because there's going to be a volume conceptually. Can you imagine that that's a volume, that's a surface, right? If you have a closed surface, isn't there a volume inside it? And all the divergence theorem says is that you find the triple integral over the volume of the vector field. So if you want to find the surface integral of a vector field, the flux, you can find the volume, triple integral, essentially, over the volume of the surface. So it has to be a closed surface, right? You can't have, you know, like an empty shell, right? It's got to have an inside to it and an outside. But most of the time, these are probably going to be spheres or rectangles. If they are rectangles, won't we use x, y, z? If this shape ends up being a sphere, won't you go to spherical coordinates? And if this shape ends up being a cylinder, won't we do cylindrical coordinates? So depends on what the volume of the object ends up being. Is it a circle? Is it a sphere? Is it a box? Is it a cylinder? Last naming, Bob.